Welcome everyone. Today we are exploring how new cardiovascular drugs are evaluated in real world large scale populations using comparative effectiveness research, that is CER. With drug development costs exceeding billions of dollars and modern studies involving hundreds of thousands of patients, clinicians, and researchers need smarter ways to determine which therapies truly improve outcomes. In this lecture, we will break down the methodological framework behind the CER, understand the major study designs used in the cardiovascular research, and learn how population level evidence shapes modern clinical decision making. Whether you are an MBBS student, MD trainee, public health learner, or clinical researcher, this session will give you a practical understanding of how large scale cardiovascular evidence is generated and interpreted. Let's begin. Now that we understand the scale of the modern cardiovascular drug development, let's look at one major problem with traditional clinical trials. Randomized control trial or RCTs are highly selective. They often include healthier patients, shorter follow-up periods than placebo comparisons under ideal conditions. But in real world, patients are very different. They are older, have multiple diseases, variable medication adherence, genetic diversity, and often receive several therapies together. So, while a trial may show that a drug works better than placebo, clinicians still face an important unanswered question: which treatment works best against another active treatment in real world populations? So, an example like SGLT2 inhibitor may reduce the cardiovascular events in a controlled trial, but how does it compare head to head with another drug in hundreds of thousands of Indian patients with heart failure or chronic kidney disease? This is where comparative effectiveness research or CER becomes essential. CER bridges the gap between the controlled trials and actual clinical practice by comparing the active treatments in large heterogeneous populations to guide the real world decision making. Let's test your research instincts with a real world CER design challenge. Imagine if you want to compare rivaroxaban versus warfarin for stroke prevention in 180,000 atrial fibrillation patients using a national claims database. Which study design would give the least biased estimate? Option A, a Naive Cohort study comparing all the users directly. Option B, an active comparator new user design with Prospensity score matching. Or option C, a self-controlled case series. Pause the video, think carefully before choosing. Remember, in comparative effectiveness research CER, the biggest challenge is minimizing the confounding and selection bias while preserving the real world relevance. At first glance, the Naive cohort approach looks incredibly attractive. You have massive sample sizes, easy extraction from insurance claims databases, and no need for complicated matching algorithms or advanced causal modeling. This is illusion of the big data, the belief that more patients automatically mean better evidence, but large data sets cannot fix systematic bias. In fact, they can amplify it. The first major problem is confounding by indication. Sticker patients may preferentially receive one drug over another, making outcomes appear different even when the treatment itself is not responsible. Next is prevalent user bias, including patients already taking the therapy, ignores early adverse events and survivor effects, distorting the risk estimates. Then comes the immortal time bias, a hidden period during which the patients must survive in order to be classified into a treatment group, artificially improving the outcomes. And finally, the channeling bias, where clinicians prescribe newer or perceived safer therapies to specific patient subgroups. So, despite the impressive scale, a Naive cohort study can produce highly misleading conclusions if these biases are ignored. Now let's visualize how these biases actually distort the real world clinical research findings. First is the immortal time bias. Imagine a prescription is written today, but the patient fills it 45 days later. In many naive study designs, that entire 45-day gap is incorrectly counted as exposed treatment time. But the patient had to remain alive and even free long enough to even fill the prescription. That means the study unintentionally creates an immortal period where the bad outcomes cannot occur, making the treatment appear artificially safer. Now let's look at the confounding by indication. Here is the comparison, which itself is fundamentally unbalanced. Warfarin patients may be older or have prior stroke and multiple comorbidities. Meanwhile, the healthier or lower risk patients are often preferentially prescribed newer drugs like rivaroxaban. So, if rivaroxaban users have better outcomes, is it because the drug is superior or because the patients were healthier to begin with? Without proper design strategies, observational research can mistake patient selection patterns for true treatment effects. So, what does a better observational study actually look like? This is the gold standard approach in comparative effectiveness research, the active comparator new user or ACNU design. Step 1, New User Restriction. We include only first time users of each medication and exclude anyone with recent prior exposure. Why? Because this removes the prevalent user bias and ensures the follow up begins at a clinically meaningful starting point. Treatment initiation. Step 2, Active comparator selection. Instead of comparing rivaroxaban to no treatment, we compare it directly against another active therapy, example warfarin. This creates group with more similar disease severity and treatment indications, improving the clinical comparability. Step 3, Prospensity Score Adjustment. Here, we estimate the probability that a patient receives one treatment versus another based on dozens of baseline variables like age, comorbidities, prior hospitalizations, medications, and many more. We then match or weight patients so that the treatment groups become balanced, almost like a pseudo randomized trial. And finally, outcome is there. We define outcomes using validated ICD-10 algorithms, perform one-to-one propensity score matching, and calculate measures such as hazard ratios to estimate comparative risk over the time. The result is a study that dramatically reduces the bias and produces evidence that is far more clinically trustworthy. Now comes the statistical engine that makes observational comparisons far more credible: propensity score matching. Think of this as forcing balance between two treatment groups. In the real world pattern, the patients receiving rivaroxaban and warfarin are often very different. They may vary in range, diabetes burden, renal function, hypertension, prior stroke risk, and dozens of other characteristics. If we compare them directly, the outcome differences may simply reflect baseline patient differences, not the drug effect itself. So instead, we build a logistic regression model that estimates each patient probability or propensity of receiving the rivaroxaban based on all the measured baseline variables. Patients with similar probabilities are then matched together across the two cohorts. In other words, a rivaroxaban patient with advanced stage, the age, diabetes, and the renal impairment is matched to a warfarin patient with nearly identical clinical characteristics. The goal is clinical balance, and we measure the balance using the standardized mean difference or SMD. An SMD below 0.10 is generally considered acceptable balance between the two groups. At that point, the cohort begins to resemble the comparability achieved in randomized controlled trials. It is important to remember that the propensity scores cannot fix unmeasured confounding, but they dramatically reduce the bias from known baseline variables and make the real world treatment comparisons far more reliable. Here's the key transformation that propensity score matching achieves. Before matching, this is an apples to oranges comparison. One cohort may be much older, having more hypertension, higher stroke risk, and significantly different baseline characteristics. In this example, one group has an average age of 75 with 80% hypertension prevalence, while the other averages 62 years with only 40% hypertension. If the stroke outcomes differ between these groups, we can confidently say that the drug caused the difference. The patients themselves were fundamentally different from the start. But after propensity score, active comparator, new user matching, or PSACNU matching, the cohorts become clinically balanced. Now, both the groups have similar ages, similar hypertension prevalence, and comparable baseline risk profiles. At this point, we are finally comparing apples to apples. That means differences in stroke outcomes are far more likely to reflect the treatment effect itself rather than the baseline patient imbalance. This is why modern comparative effectiveness research CER relies heavily on careful cohort construction and matching strategies. The quality of the comparison is often more important than the sheer size of the database. Now, let's zoom out and place CER into the bigger methodological landscape. These are the four major frameworks that dominate the modern clinical evidence generation. First, RCTs, randomized controlled trials, remain the gold standard for causal inference. Randomization minimizes the confounding and gives extremely high internal validity. But RCTs are expensive, highly selective, and often fail to reflect the real world patients. That makes them excellent for proof of concept, but sometimes limited for everyday clinical decision making. Second is PSACNU framework, Prospensity score active comparator new user design, which we have focused on throughout this lecture. Its major advantage is ability to compare treatments head to head in massive real world populations. This provides strong external validity and highly practical post marketing evidence. However, it is still not fully eliminate unmeasured confounding. Third, we have instrumental variable methods and Mendelian randomization approaches. These are especially valuable when hidden confounding dominates the dataset. If a valid instrument exists, these methods can recover the stronger causal estimates from observational data. The challenge is that finding a truly valid instrument is often very difficult. Finally, target trial emulation, one of the fastest growing areas in epidemiology. Here, the researchers expertly design observational studies to mimic every component of a hypothetical randomized trial. Eligibility criteria, treatment assignment, follow up, outcomes, and censoring rules are all pre specified. This creates extremely rigorous observational analysis suitable for policy modeling and modern regulatory science. The key takeaway is this: no single framework is universally superior. Each method solves a different problem, balances different biases, and answers different clinical questions. The best researchers understand not only how to run these methods but when each method should be used. CER is only as powerful as data infrastructure behind it. And today, modern CER is built on massive real world data ecosystems. The first major source is administrative claims databases. These include systems like Medicare, MarketScan, and CPRD in the UK. Claims data capture prescriptions, diagnosis, procedures, hospitalizations, and long term outcomes across millions of patients. Their biggest advantage is scale and longitudinal follow up. The second pillar is electronic health record repositories. Platforms like Epic Cosmos, Trinextix, and IQVIA integrate the real clinical information directly from hospitals and healthcare systems. Unlike claims data, EHR datasets often include laboratory values, imaging results, vital signs, and physician documents. These provide much richer clinical detail for advanced analysis. Third are biobanks and genomic databases. Resources like UK Biobank, BioMe, and all of us combine clinical data with genetics, biomarkers, and molecular profiling. These databases are driving decision precision medicine the medicine and enabling the modern causal interference methods like Mendelian randomization. Fourth are disease specific registers. Examples include cardiovascular registers like AHA GET with the guidelines and CAT-PCA. These databases focus deeply on one disease domain and often contain highly validated outcomes. And the procedure details. At the center of all the systems sits CER analysis, integrating the diverse real world data sets to answer clinically meaningful questions at scale. And importantly, India is building its own clinical world database ecosystem. Initiatives involving CIDISCO, AIMS Network, NPHCE programs, and state insurance databases are creating enormous opportunities for population scale clinical research. The future of evidence research generation will not rely on a single data set. It will come with the intelligently combining claims data, EHRs, genomics, and registries into an unified analytical frameworks capable of studying medicine in the real world. One of the biggest misconceptions in medical research is that randomized controlled trials and comparative effectiveness research compete with each other. In reality, they work together. They are complementary systems in the modern evidence ecosystem. RCTs are designed to establish the efficacy under highly controlled conditions. They answer the question like, can this drug work under ideal circumstances? CER, on the other hand, answers a different question. Does this therapy still work in the complexity of real world clinical practice? A perfect example is the EMPA-REG outcome trial between the 2015 and 17. This landmark randomized trial demonstrated cardiovascular benefit with empagliflozin in patients with type 2 diabetes, but clinicians then needed to know whether this effect would remain consistent across the diverse real world populations. That is where CER stepped in. The CVD real study analyzed more than 3 lakh patients in routine clinical practice and confirmed that the cardiovascular benefits extended beyond the tightly controlled trial settings. This helped establish the concept of SGLT2 class effect in real world medicine. The same pattern occurred with the COMPASS trial evaluating the rivaroxaban plus aspirin. Randomized control trials demonstrated efficacy first, and then CER studies validated how these findings influence the real world prescribing policies and population outcomes. Similarly, the Fourier and Odesky PCSK9 inhibitor trials showed major reductions in the cardiovascular events. Subsequent Medicare based real world analysis confirmed meaningful MACE reductions outside the trial environments. This is the modern research pipeline. RCTs generate the initial signal, CER test whether the signal survives the complexity of the actual healthcare systems. So the relationship is not the competition, it is a symbiosis. RCTs prove the efficacy and CER proves the effectiveness. By this point, we have seen how powerful the comparative effectiveness research can be, but the observational research always comes with one major challenge bias. That's why high quality CER studies require an entire diagnostic toolkit designed to detect, minimize, and stress test potential biases. Let's start with confounding by indication. This occurs when sticker patients are preferentially given certain therapies. If we ignore this imbalance, the treatment may falsely appear harmful simply because the patients were already at higher baseline risk. To defend against this, the researchers use techniques like propensity score matching, inverse probability weighting, and instrumental variable analysis. These methods attempt to recreate the balance normally achieved through randomization. The second major threat is immortal time bias. This happens when the patients must survive long enough to actually receive the treatment. Naive analysis mistaken this waiting period as protected exposure time, artificially favoring the treatment group. To correct this, investigators use time conditional propensity methods and as treated analysis that properly align the exposure timing. Third is the outcome misclassification. Real world databases rely heavily on ICD coding systems, and inaccurate coding can distort the outcomes. That's why validated outcome algorithms with high positive predictive value are essential for the credible CER research. Another important issue is depletion of suspectables. High risk patients often experience events early and leave the cohort, making them remaining population appear artificially healthier over time. Landmark analysis helps reduce this distortion. Now look at the forest plot on the right. This represents the sensitivity analysis, one of the most important concepts in observational epidemiology. Researchers repeat the analysis multiple times using different assumptions, models, and definitions. If the hazard ratio remains stable across all the scenarios, the findings are considered robust. Notice how nearly all the estimates clusters around a hazard ratio of approximately 0.85 and remain consistently separated from null line at 1.0. That consistency strengthens the confidence in validity of the result. And this leads to one of the most important principles in CER. A trustworthy observational study does not simply report one answer, it proves that the answer survives repeated attempts to break it. Here's a classic exam style question that brings all the concepts together. A researcher uses a national claims database with 200,000 atrial fibrillation patients to compare the stroke outcomes between rivaroxaban and warfarin initiators. Now focus on the methodological details. She matches patients using Prospensity scores across 90 covarieties, restricts the analysis to new users only, and performs one-to-one matching between treatment groups. This is not a randomized controlled trial because treatment was not randomly assigned. It is not a self controlled case series because patients are not serving as their own controls. And it's definitely not an ecological study since the analysis is performed at the individual patient level. The correct answer is active comparator new user cohort design, which is also known as ACNU. Why? Because the study compares two active treatments head to head, includes first time only users, and uses propensity score matching to create the balanced cohorts. In modern comparative effectiveness research, this design is considered one of the strongest observational approaches for estimating the real world treatment effects. Before we conclude, let's review some high yielding terminology that frequently appears in the research papers, grant proposals, and PIVA discussions. First, active comparator. This means comparing one drug directly against another active treatment instead of comparing against placebo or no treatment. Doing this reduces confounding by indication because both groups usually have similar disease severity and clinical indications. Next, new user design. Here, researchers include only patients who are starting treatment for the first time. This avoids prevalent user bias and survivor bias, making the groups more comparable from the beginning of follow up. Third, propensity score. A propensity score is the probability of receiving a treatment based on baseline characteristics, typically calculated using the logistic regression. It helps create balanced treatment groups that resemble randomized trial populations. Now, target trial emulsion. This is a modern framework where researchers first design the ideal randomized control trial they wish they could perform, and then try to mimic that exact protocol using the observational real world data. And finally, the negative control outcome. This refers to an outcome that biologically should not be caused by the treatment being studied. If the analysis still shows an association, it suggests a residual confounding or hidden bias in the study design. Together, these concepts form the methodological backbone of high quality comparative effectiveness research, that is CER. Let's close with the single most important message from this entire discussion. Randomized controlled trials are powerful for proving the efficacy under ideal conditions, but the patients in real world are rarely ideal. They are older, have multiple comorbidities, take several medications, and often don't fit the strict trial criteria. Next is that's what where the comparative effectiveness research becomes essential. Real world evidence helps us understand how treatment actually performs in everyday clinical practice across diverse populations, healthcare systems, and long term follow up. But the key lesson is big data alone is not enough. Without proper study design, observational research can become dangerously misleading because of hidden biases and confounding. That's why modern methods like active comparator, new user designs, propensity score matching, sensitivity analysis, and target trial emulsion are so important. That's why they help transform the observational data into clinically meaningful evidence. So, when designing your own research, don't just ask, can I analyze this dataset? Ask, does this design truly answer the clinical question patients care about? Because ultimately, the goal of research is not just statistical significance, it's the better discussions for real patients in the real world. And it is also better decisions for real patients in the real world. Thank you everyone for joining this session on CER Comparative Effectiveness Research and Real World Evidence Methodology. We explored how observational data can transform into meaningful clinical evidence using strong epidemiological design principles. From understanding major biases to learning active comparator, new user designs, propensity score matching, and target trial emulsion, these tools are becoming increasingly more important in modern medical research. I hope this session helped simplify the concepts that often seem technically overwhelming. If you found this useful, feel free to share it with your colleagues, classmates, or research teams. And remember, good research is not just about having large data sets, it is about asking the right clinical question and choosing the right methodology to answer it. Thank you once again, and all the best for your future research and academic journey.